Welcome everybody to this dual channel component characterization demo. My name is Florian Ramian and I'm an application engineer with Rohde Schwarz for signal and spectrum analyzers. So this demo is about characterizing a high power PA. And basically what we see here in the block diagram, we have a vector signal generator that provides the stimulus, in this case a wideband modulated signal. We have two amplifiers that I'm going to focus on in a minute, and we have the FSWX signal and spectrum analyzer as the receiver of the output signal on the right-hand side. So why do we have two amplifiers in this block diagram? The first one, of course, is the device under test itself. This is what we want to characterize in the end. However, as I said, this demo is all about a high power PA, and in high power PAs require very high input power because they amplify on a high power level. And in that case, very often we need so-called driver amplifiers that amplify the signal from a vector signal generator so that it matches the required input power to the device under test. And unfortunately, in this case, we have two nonlinear devices in our block diagram, but the ultimate measurement challenge is to measure the DUT only, not the two amplifiers. And the solution is to compare the output of the device under test directly to the input of the device under test. Not to what the signal generator on the very left-hand side is providing, but to exactly the signal that's going into the device under test. Now going back to a very simplified block diagram of the FSWX, we see two fully symmetric channels here. And if I stop my little animation, you can see the two signals on the two paths traveling in parallel on these two fully symmetric channels before reaching the ADCs and being handed over to whatever measurement application we want to use it in. And with that, let's go right into the demo. So before we go into the measurement details, let's have a look at the measurement setup itself. So we do get a fully modulated signal coming out of the vector signal generator and going into our driver amplifier here on the right-hand side. Next step is a coupler. The main output of the coupler goes into the actual device under test itself. And then from the device under test itself, we go into the RFA port of the FSWX, and the coupled out signal from the coupler goes into the RFB port of the FSWX. Now let's have a look at the measurement itself. For the beginning, we are looking at the spectrum analyzer measurement of the output signal of the device under test. We can clearly see it's a fully modulated signal, 100 MHz of bandwidth in this example. And we can also see the device under test is operating in its nonlinear region, since we have the spectral regrowth or shoulders here to the left and right of the transmit signal itself. And with that, let's go into the amplifier measurement personality and let's have a closer look. At the moment, the amplifier measurement personality is configured to read the input signal that it uses for its comparison from the vector signal generator. So we have a control, a LAN control to the vector signal generator. We can query, for example, the input power, and more importantly, also the so-called reference waveform is directly queried from the signal generator. Here, the measurements that I have configured for this demo is an AM/PM plot on the upper left-hand side, a gain compression plot on the upper right-hand side, a spectrum plot that shows in yellow the output spectrum and in green the input spectrum, and we have some numerical results such as the EVM, which is 5.6% roughly in this single channel measurement. So at the moment, personality runs in its traditional mode, the single channel measurement, shows a gain of 17.5 dB, and we can see the crest factor through the dot reduces by 2.3 dB. The next step is we have built into the amplifier measurement personality a new mode of operation that makes use of the dual channel architecture of the FSWX. Configuring the second channel or the live reference capture is straightforward. Instead of reading the reference from the generator, we'll just click on Capture the Reference, and it will automatically turn on the second RF channel. And if we have a look at the details, we can see that the AMPM plot and the gain compression plot show less nonlinearity. Also, the cloud of the measurement points gets more narrower, which means we have less frequency response when we directly compare the output against the input. As a consequence, if you look at the EVM number, it's significantly reduced from 5-point-something% to 2.8% roughly. And at the same time, you can see power in is roughly the same. It's off by 700th of a dB, so we can declare it the same. In the same way, gain is the same. However, what is different and what is probably relevant for your evaluation of the device and the test is we can see the signal going into the device has no longer a crest factor of 10 dB, but only 8.8 dB. Because our driver amplifier in this case also operates in its nonlinear region and also compresses the signal. So the actually compression inside my device and the test itself is only a little over 1 dB. And thus also the huge difference between EVMs in single channel mode and dual channel mode. So in dual channel mode, we can clearly focus on the DOT only and exclude all the unwanted other components in my measurement setup that otherwise would have an effect on the characterization of my device in the test. So this was the live demo of the high power PA measurement where we directly compared the output signal to the input of the device in the test. And as you could see, the EVM significantly improved when we compared directly the output to the input, as well as we got a more realistic measurement of the P1 dB and also of the crest factor. So a dual channel component characterization setup can provide significantly better results for your device in the test.